A person who gives a talk is really only a spokesperson for great teams that provide the information that that person's going to communicate. And so in acknowledging those people who really make the Terzaghi lecture work, I like to recognize my colleagues at Cornell, students, professors, lab managers, Harry Stewart, Tim Bond, and a whole variety of students who have done such a great job and have contributed to this. Their pictures are up here, and they certainly deserve the recognition of providing a lot of the information that you're going to hear about this morning. I also like to thank the National Science Foundation that supported Cornell and many other universities with needs to provide large-scale testing laboratories to understand the behavior of soil and structures over the last decade, and for supporting the current program, NERI. I think Ellen Rashi is going to have a program this morning where she talks a bit about the whole NERI process, and you should go and listen to that. I'd like to also thank some of our great colleagues at Rensselaer and University of Buffalo. Rensselaer, Tarek Abdoun, Ricardo Dobry, receiver of the Peck Award yesterday, and Mike O'Rourke, who have done such a great job coordinating with us over the year. Mike Simmons also. We've had a great collaboration. You'll hear some information today and some data that they also were responsible for. So thank you so much. There's also a lot of people who contributed to this lecture, provided information, and I'd like to thank them. Not all of it will be presented here. I had to, because of time restrictions, leave one part of the lecture out, which is on tunneling, ground movement effects, and their influence on various pipelines. That will be in the published lecture when that time comes. So I'd like to start then by showing this picture of the Denali Fault crossing. This is where the Trans-Alaska Pipeline crosses the Denali Fault, and in the 2002 Denali Fault earthquake, this pipeline moved with the fault without being damaged 18 feet and 2 feet vertically. But to do that, they had to take it out of the ground. And there are many pipelines that we have to work with in our society that we can't take out of the ground. And so understanding how they perform under ground deformations is really the topic of this particular lecture. And in this lecture, I'm going to cover these 7 topics. I'm going to start with underground assets. And to begin with, you're probably sitting on a pipeline. And if you're not sitting on a pipeline, by the time you leave here and walk back to your hotels, you probably will have crossed dozens of pipelines. There are about 300,000 miles of gas and liquid fuel transmission pipelines in the United States, over 1.2 million miles of gas distribution. There's 67 million gas services. There's nearly 1.2 million miles of water distribution pipelines, and the AWWA has come up with a recent survey indicating that we have about $2.4 trillion of pipeline replacement assets in the ground. There's about 1 mile of pipeline which is constructed every 15 minutes in the United States, and about 1 mile of pipeline every 3 to 4 minutes worldwide. Clearly, there are a plethora of pipelines around that are very important with respect to soil-structure interaction, a true interface between structural engineers and geotechnical engineers. Let's look a little bit about that inventory for a minute. What I have up here are bar charts showing the percentage of the system associated with various pipeline diameters for 4 major water supply companies, including the New York Department of Environmental Protection, the Los Angeles Department of Water and Power. And there's a very interesting statistic here that about 90 to 95% of all of these are in sizes which are less than or equal to about 24 inches. In fact, LADWP calls their distribution pipelines anything less than 24 and their trunk lines anything larger. Similar statistics can be gotten from the PHMSA, Pipeline Hazard Material Administration, and they have done statistics on the gas distribution pipelines in the United States. 99% of them are less than or equal to 24. The larger ones, of course, are some of the greater and more important ones, but just to get the statistics right and a sense for the composition of the systems, I thought I'd lay these out because we'll show how they become important later on. This is one of the favorite pictures I like to show. This was provided by the Consolidated Edison Company in New York City, and this shows the corner of Wall Street and William Street in about 1920. And you can see what the underground infrastructure looks here. Now that's the New York Stock Exchange in the background, and this intersection with the various pipelines is pretty representative of a lot of areas that I know about in urban areas that have these enormous amounts of pipelines underground. So just look at that. That is the national treasure. Those are the pipelines that are going to convey the services and the resources that make modern societies work, and they're an absolute mess. This is a wiring diagram. Look at the incredible complexities of the pipelines there, and like any treasure, we bury it underground and then forget about it for ages until there's a problem associated with it. Pipelines are part of a national challenge to be able to manage and understand and work with our infrastructure and to make it a better infrastructure. And these are some of the issues that we have to deal with when we're going to work within this space. You'll see in this next picture a photograph taken in about 2005 when they were reconstructing Lower Manhattan after all the damage that was done during 9/11. And you can see that the pipelines have become newer in the replacement zones, but still very complex and closely related to each other. It's not hard to imagine that a damage to one of those cast iron water mains or gas mains would break and affect an adjacent pipeline, and that would cascade to have system-wide effects. And that frequently happens in New York when the city is shut down, when these facilities don't work. This is a picture from a TV camera in Korea. And this was a pressure test on water pipelines to determine their integrity. And unfortunately, some of the pipelines weren't up to snuff. So there's another example of the aging infrastructure and some of the challenges it presents. Look at these two poor fellows on the bicycle. I don't ever know what happened to that first one, the second one there. That is the system that we face before we have an earthquake, or before we have a hurricane or a flood, or before we have landslides. We also are going to have ground deformation effects associated with tunneling and deep excavations, and a whole variety of causes for subsidence. And the work that's been done and supported by the National Science Foundation and others on the effects of earthquakes and other extreme events on soil pipeline interaction has not only value for extreme events, but it has value for everyday performance of pipelines which are subject to the effects of ground movements from tunneling, deep excavation, subsidence, and other kinds of disturbances. So this kind of investment and this kind of activity goes a long way to helping us understand and to engineer better for what's underground. Whenever we talk about extreme soil pipeline interaction, there are two aspects of it which automatically come to mind: material and geometric nonlinearities. And this is a double-edged problem because not only do we have material and geometric nonlinear properties for the soil, but simultaneously we have material and nonlinear geometric properties with respect to the pipeline also in the structure. So this is a real challenge, and probably the greatest challenge are the geometric nonlinearities, because when pipelines deform, when the ground begins to fail along specific failure planes, you actually have a complicated and complex behavior that results. So I'm going to start on the technical part of this talk by looking at where the rubber meets the road, and that is where the soil and the pipeline meet. We were able to perform some large-scale experiments at Cornell. This is an aerial view of a 16-inch diameter high-density polyethylene pipeline being deformed without the soil in place. So you get a sense for how the pipeline is deforming, it's stretching, it's bending. You can see that there with those reaction blocks that are mimicking the reaction of the soil. And if you keep that image in your mind, the next one is going to be the soil, which is being ruptured and sheared in terms of a left lateral strike-slip fault and its effect on the underground pipelines. Well, if we freeze frame that for a minute and look at the interface here, we get a lot of lateral displacement. In fact, the failure mode for the high-density polyethylene pipelines is a squeeze-off failure. These things actually can sustain quite a bit of tensile deformation. They're extraordinary. We'll see some examples about that later. But they will eventually squeeze shut and that'll be a function of what kind of pressure they're carrying. But often in an extreme event, we can't rely on the line to have pressure in it because it could lose pressure from a variety of different operational or other failures areas in other parts of the system. So they really need to survive with low or zero pressure if they're going to maintain their integrity. We studied these pressure distributions by using these tactile pressure sensors. These were introduced to us by Tarek Abdoun at RPI. We were able to make them work in these large-scale tests where there was great deformation and distress on them. This is a picture of one of them with one of our lab technicians. It's Joe Chipolowski. There's about 2,000 sensors. These are electronic sensing units which will have voltage drops, which when we monitor them, we can come up with a pressure distribution and therefore actually measure the pressure distribution around nonlinear objects like pipelines under large ground deformation. We ran some very well-controlled large-scale two-dimensional tests. These are some plan and profile views where we actually put pipelines in a box. It was about 2.4 meters wide and about 1.2 meters deep. So the end effects were minimal, and we actually provided for very low resistance ends. So we could get a really good plane strain, force, displacement, maximum force relationships out of these tests. We could get the pressure distributions from the tactile pressure sensors, and we could validate those because we were actually measuring with the load cells the actual loads in the pipe, and we could correlate the pressure sensor loads with the actual measured loads. And one of the things we want to do is when you get that kind of a test measurement, you're getting a normal pressure on the pipe, which is illustrated by this picture here. And if you want to break that down into the horizontal pressures, then you have to decompose the normal force, which also generating a frictional force on that pipe. So there's a double decomposition to get the horizontal components, which is illustrated in this particular diagram. You can integrate this. Now, this is an equation that was originally developed by Mike O'Rourke, so I want to recognize him for doing that. We used it as our research team. It shows here you can integrate the horizontal components from those components which are perpendicular to the longitudinal axis of the pipe from the normal force and also from the frictional force. And you can also do this in a numerical fashion by using the actual tactile pressure sensor data, which is the second equation there. And here's some examples of the pressure distributions that were monitored during some of these two-dimensional plane strain tests. What you can do with those data is you can take the data, you can put it into some form of that regression will fit the sinusoidal distribution of the data and be able to tag that with some moniker or metric of the statistical substantiation or stability of that. So we have an R squared of about 0.96. You can see the black regression line. It's a very well-defined sinusoidal distribution. You can see the data ranges. We have about 17 or 18 different data sets shown in this particular slide. And I think what's also quite interesting, and we'll come back to this later, is that there's numerical analysis that we've done. You can do the same thing with those. You can take the normal distributions to those and decompose those into the horizontal components. And they actually show a very good relationship too. So in this particular slide, what we've done is we've plotted the normalized pressure distribution. That is the pressure distribution divided by the maximum pressure, and you can see the good fit with respect to the sign. For lots of numerical reasons, when we roll these things up and do analyses, it becomes useful for us to be able to define what we would call an apparent frictional force, which would be generated by the horizontal force in this case, that P sub h, multiplied by the tangent of delta, where delta is the angle of soil pipe interface friction, rather than to do the stress normal to the surface. We have two ways that we can decompose our forces. We can decompose them perpendicular to the longitudinal axis of the pipe, or we can decompose them perpendicular to the surface of the pipe. But it's the one that decomposes perpendicular to the surface that generates the frictional resistance longitudinally. So if we want to couple all of this stuff, this is the way you couple it. You look at the relationship between the actual friction, which is longitudinal, that's the F sub t, and the apparent friction, which would be generated by the forces which are perpendicular to the longitudinal axis, and we can plot those because we've measured them very precisely, and this is the transfer function that you get. You can use this dimensional value, it's plotted as a function of the interface friction angle there, and you can see that if you're testing a high-density polyethylene pipeline, which is going to have a tan delta of around 0.4 or 0.5, you don't need a correction. The two of them are virtually identical. But if you're looking at a pipeline that has a very high delta, which is going to be a tangent of delta close to 1, you're going to have a situation here where that's a very rough surface, and you're going to be sort of overly conservative if you use the horizontal force to evaluate your friction. So the first thing we learn is from this ability to look at the interface, where the rubber meets the roll between pipe and soil, that we need to account for the coupled transverse and longitudinal soil forces. In the Terzaghi paper, we'll talk about how you can do that in one of the readily available softwares, Abacus. But basically, you create these gap elements which are linked in with your force relationships between the pipe and the soil, which are perpendicular to the longitudinal axis of the pipeline. And you couple it by virtue of the true friction normal to the surface of the pipe, so that now you are truly in a two-dimension accounting for the coupled forces perpendicular to the longitudinal axis and the frictional forces which develop longitudinally. And if you don't do that, you will not have a right answer, and you can be very far off and unconservative in the process. So, first lesson. Soil pipe interface, relationship between soil force normal to the pipe surface versus force normal to the pipe longitudinal axis is key for modeling coupled soil pipe interaction, and the evaluation of friction along the pipe from soil force normal to the longitudinal axis, we have provided a way in which to account for that. Next topic is soil pipe interaction, pipeline interaction. And to deal with this, we have a number of different ways. We can look at the pipe as a beam, as a kind of a quasi-L pile, if you want, that's going to be in a horizontal direction. And we can characterize interactions. Now, I don't want to call these springs because they're far more complex than that now. They're nonlinear. They can account for strain softening behavior. You can pack a lot of detailed soil structure interaction to these interactions, or you could also make it very simple and make it a spring. But we have the capacity to go far greater and do a much more sophisticated job than that at this point. So we can replicate very complex interactions in the pipe and in the soil. And then there's also 3D continuum modeling, which is going on. It's evolving. There's still challenges, but there's been some extraordinary progress made in the three-dimensional modeling, too. So this is a kind of a summary slide, kind of putting some of this into perspective. It's obviously selective. It's not going to recognize some good work from some good people, but this is the amount of time that I have available, so I'll illustrate some of these things. We can actually look at the pipeline not as a beam. You can look at it as a shell. And so you have shells which can be connected to these soil pipe interaction relationships, which are shown here by those graphics that are attached to the shell. And then there are a number of very interesting works. Our colleagues at RPI and ourselves, with Xi et al., it's a paper in ERI in 2013, looked at a variety of different types of ways of modeling three-dimensional pipelines in solid soil conditions, modeling the pipe as a shell element, modeling the soil as a solid. Recent work, Robert et al., this is work that we did with the folks at Cambridge, Kenichi Soga, Dylan Robert, I should say, is a professor at RMIT in Melbourne, Australia, and looked at a variety of different three-dimensional shell modelings, and some excellent work in by Vasouras in Greece, looking at some of these three-dimensional soil pipe interaction conditions. When we characterize the strength of soil, we have always liked to use direct shear tests. And the reason for that is because we're interested in these two-dimensional plane strain reactions where we actually can get very good experimental data to validate what we're coming up with numerically. When you run a direct shear test and you do a careful job of it, and that's a key right there, you recognize that, number one, the direct shear relationship between shear and normal stress is not the plane of tangency to the pore circle. It occurs off that. It is a line of zero extension. And if we go back to great research that have been provided by our British colleagues, we know that there's coaxiality between strain, more circle of strain, and more circle of stress in a direct shear test. And owing to the great work of Davis and others from Australia, you actually can, from a direct shear test, show what the plane strain angle of shearing resistance and actually develop a relationship between the two. So from one test, we can look at the direct shear conditions of failure in soil, and we can look at the plane strain conditions where we actually are going to get the point of tangency to the yield surface if you want to define a more Coulomb yield surface for this, for example. So it's a very powerful test. And also when you recognize that failure of the soil along the longitudinal axis of the pipe is also a surface of zero extension, you actually have a test that can actually provide relevant strength data for the interface as well as for the soil structure surrounding the pipe. We performed tests because we come from an area that was glaciated, and believe me, when we left Ithaca, it was 16 below zero. I think the glaciers were coming back. We deal with glacial fluvial sand. I'm showing some of the characteristics there. I'm showing some of the types of direct shear boxes that we use. We use large ones, 100 millimeters, 300 millimeters in diameter. And we decided to characterize the sands as medium, dense, and very dense. And those are associated with direct shear angles of shearing resistance varying from about 35 to 43 degrees. But when those are converted into plane strain, they go from about 41 to 49. So these we're taking as emblematic or as representative of granular material. That's because these are the kinds of soils that we looked at. We looked at them fundamentally, but they still have specific characteristics, which you see up on the screen. And then we developed some two-dimensional models for these plane strain tests that we ran. This is just showing a picture of one of these plane strain tests. Our analytical model worked off a more Coulomb yield surface. It had strain-compatible modulus, and we also had a special subroutine in there for strain softening from peak shear, so it could account for strain softening situations. And if we show the next slide, you can see some of these simulations with the pipe being pulled laterally through the ground. And if we freeze that and we look at some of the testing, you can see that the pipe pulls away from the soil in the analysis, and also in the tests, the pipe pulls away and leaves a void, particularly when we're testing the way we do with partially saturated soils, which are really the right representation for the soils that we're going to account for in practice. In fact, when we compare the analytical results with the experimental results, there's been excellent agreement, not only for these tests associated with lateral pipe-soil interaction, but also vertical upward pipe-soil interaction, even to the extent we've developed a sort of an auto-remeshing situation where you account for as the pipe is moving up in the soil, as it's beginning to punch out of the ground, the reduction in vertical force up there, and the way that relationship between pipe force and displacement should look. So we can roll these up, and these have been published in various journals, including the Geotechnical Journal, Geotechnical Geoenvironmental Engineering Journal, and the Canadian Geotechnical Journal. And we can show these dimensionless forces, which are the forces we measured, divided by the unit weight of the soil, the depth of the center line of the pipe, the diameter of the pipe, and the length of the pipe. And if we take the length as a unit length. You can get the force per linear distance. And we plot these relative to a dimensionless depth, which is the depth of center line divided by the diameter, and can come up with relationships that allow us to be able to predict what the maximum forces are going to be on the pipe. Now, there's something really interesting in this picture, particularly the one that's on the left, because what you'll see in that orange line are the partially saturated tests we performed at Cornell, along with the dry soil tests. And for the same soil with the same dry density, you can see that the partially saturated medium dense curve is higher than the partial density dry sand curve. And so suction in the soil is contributing an additional 20% to the load. And that's something that's generally not recognized or neglected when we go through and we account for this interaction between the pipe and the soil. We can go further with this model, having validated it in the two directions that we've tested intensely and feel comfortable with the model. We now can look at pipe-soil interaction in the vertical direction downward, in the oblique directions. We can do a full 360-degree sweep to be able to come up with a characterization of the soil-pipe interaction for any direction at any depth in the soil. And that's what we did. We started off with the vertical, and when we ran the vertical, you can see on the left-hand side the dimensionless force plotted with respect to the dimensionless depth for the vertical reaction, and then we also could compare that vertical reaction with the conventional bearing capacity equations, which are very often advocated and used in design. And we did that. We found out that systematically the actual forces that we were modeling were less than what's given by the conventional bearing capacity formulations. And this was an observation also made at RPI based on some of the centrifuge tests that they did for normal fault interaction, where they had suggested reducing the conventional bearing capacity formulations by about 1/3 to, and sometimes as high as 1/10. So we certainly can validate that particular experimental observation from our colleagues and show that, in fact, there is a lower resistance, and we factor that into our results. And I must say that these are partially verified experimentally, and that's by centrifuge test, and certainly make good sense to us from a numerical simulation point of view, but this is an area where we could actually use some large-scale validation also to finally ice this particular pursuit. However, taking that, which is interesting, we also can look at the oblique soil pipe interactions. These are 45 degrees downward, 45 degrees upward. And we actually could run through all of these different orientations numerically, and we can characterize the force that's generated as a maximum against the pipe for any interaction mode. That's what that I sub m stands for in that equation. And we can characterize that by virtue of this dimensionless number, this NQIM multiplied by the effective stress unit weight of the soil, the height or the depth to the center line of the pipe, and the diameter of the pipe. And what we found, if you look at this, for example, as a sort of random orientation, is we actually can account in an equation, and this equation actually comes from work that was done by Ken Nyman, who borrowed this from Meyerhoff. You actually can only need to define the force on the top of the pipe, that is the vertical upward, the lateral, and that's the same in both directions, and the base. And by these equations, you can account for the variation in maximum load 360 degrees around the pipe. So you even can boil this down to a set of very easy manipulable equations by just knowing what the reactions are at 4 points around the circumference of the pipe. And that's really a significant recognition. These are showing a kind of summary of these analytical results for the ratio of the N sub Q, that is the reaction, dimensionless reaction number for the pipe in any direction, normalized by the horizontal, because we have so much good horizontal data from the large-scale tests. And what you can see over on the left-hand side is the 360-degree plot of that ratio. And you could see when the Dimensionless depth is shallow, so that HC over D is 3.5 in that upper left-hand corner plot. You can see that it's very asymmetric distribution, 360 degrees around the pipe. Because you're so close to the surface, the uplift force is very small when normalized with respect to the horizontal, and the vertical is still pretty high. But as we continue to go deeper through the soil, you can see that by the time we're getting to depth to diameter ratios of around 30, you're getting into a circular, and then finally you have a circular uniformity where at depth you should not be able to distinguish horizontal from vertical and whatever. So we have the opportunity now to have a comprehensive methodology that looks at the interactions in the full 365 degrees. We also can characterize the force displacement relationships by using rectangular hyperbola. That's a great way to fit nonlinear things. We use it all the time. And in the Terzaghi paper, you'll see that we've provided equations predicated on this rectangular hyperbola to characterize the force displacement relationship as well as the maximum force in any given direction at any given depth. Now that brings me to soil suction. We depend upon soil suction all the time for the stability of the ground, because if everything was dry, we would have just the friction we were supposed to have, right? But really what happens is we live in the vadose zone. Many, many areas will have partially saturated or unsaturated soil conditions, and that apparent cohesion keeps things going. It's when that breaks down that we actually get some surprises, and we get some landslides and things of that sort at times. That works to our benefit, but when we're characterizing the reaction between pipes and soil, it works to our detriment because it adds to the resistance. So the most recent work that we've done with our colleagues at Cambridge, with Dylan Robert and Kenichi Soga and others, allow us to develop a simplified way to guide us in terms of accounting for the effects of suction. And I'm going to show it to you right here in this colored chart. On this chart are the class 2 and 3 boundaries of fill in the ASTM recommendations or standards. So if you're using class 2 and 3 fills, which are specified for burial of pipelines, those are the black lines. As you get smaller and smaller grain sizes, so as the grain sizes goes from the left to the right, your potential for suction goes higher. Now what we did in our models is we defined it for the degree of saturation and maximum suction. I don't know what the degree of saturation is going to be for your pipe in the field. So we defined it as a maximum to get the worst case, and then you have to use some engineering judgment or some additional evaluation from there to account for the suction effects. But you should never neglect them. And for example, if you look here, if we go to the low zone, in this case, the soil pipe reaction force may be 1.2 times higher for the soil suction conditions. Going over to that red zone, it could be 2 to 3 times higher. One of the practical benefits from this curve is that if you go to the left of the blue zone, none of that develops suction any higher than a dry sand. So you don't need to make any corrections, and if you want to dig a trench which has sloping sides to it and fill it with material that have those characteristics, then you're not going to get suction effects. If you get into the fighter grade size, you do need to consider suction and take that into consideration. This leads us to a design chart where we specify various characteristics for the pipe, and we ask ourselves, given the dimensionless depth, does the pipe size have any effect? And of course it does. Because if you were to take a depth to diameter ratio of 2, and you were to have a 1-foot diameter pipe, you'd then have a depth for that pipe of 2 feet. If it was 6 feet, it would be 12 feet. The confining stress with depth suppresses the angle of dilatancy, and therefore your peak shearing resistance will decline. Our model accounts for that because through direct shear we break this all down into the angle of dilatancy components for different levels of stress and so forth, and those corrections are shown on those graphs which I'm presenting here. In the upward direction we don't see the effect. For the downward direction we see a significant effect, and for the horizontal it's important to consider many of the times. So now we go back to taking this model and looking at it from an experimental validation perspective. If we look at some of our large-scale tests of a 250 millimeter diameter high density polyethylene pipe. What I'm showing here are the measured experimental results relative to the analytical results if you didn't consider the coupled soil friction normal force relationships. That is, if you just took the K0 conditions that are in the pipe prior to the ground rupture event. And you can see that they are under-predicting. When you couple those forces, and these are left lateral strike-slip fault experiments, they are going to generate a lot of force normal to the surface of the pipe, and they're going to amplify the friction where that normal force is occurring. When you couple the two, you properly account for that amplified friction and therefore the strain attenuation that has to occur at the center of the ground rupture. So when you do that, you can see that the measurements come into very good agreement with the coupled analytical results. Similarly here, these are other tests that we ran looking at the difference between partially saturated and dry sand. You can see that in that 250 millimeter diameter test, the partially saturated model over-predicts a little bit the maximum axial, but it actually does a better job of predicting the bending strains. You can always break this performance of the pipelines down into their axial performance and into their bending performance. And then the test that you see on the right-hand side of this projection is a larger diameter pipeline, a 400 millimeter, 16-inch diameter pipeline. Your data are missing in some locations because we had tactile pressure sensors there. And again, you get a good agreement between the measurements and the actual analytical results. We also looked at a test that was written up in the Derzaghi et al. 2013 test. This was a normal fault, a movement effect. And we reanalyzed this with a two-dimensional model that accounts, number one, for the appropriate bearing being reduced, that accounts for the coupled soil pipe interaction, that does a better job of accounting for strain softening effects for upward pipe movement, which is going to occur on the down thrust side of the fault. And then also looking at the fault displacement not as an abrupt movement, but because when you develop a Rankine zone there, anytime you have a normal fault, you're getting an active condition as the down-thrown side moves relative to the up-thrown side. If you distribute your movement across that zone, and that's consistent with the photograph that we just saw, you get an excellent agreement from the two-dimensional that compares very well with the three-dimensional analyses that were shown on this diagram and which were done and presented in that paper. So lessons, soil pipeline interaction. We have an integrated methodology for soil pipe interaction for all pipe movement directions and depths where the diameter, that should be the height relative to the diameter, not the diameter relative to the height, greater than. There's always a typo somewhere, always. So this is the one. I hope this is the last one we see. That should be HC over D. So simulations show that vertical downward soil pipe reaction forces are about 1/2 to 1/3 the conventional. That's a very important observation. And of course we have to account for suction enhanced soil pipe forces. Now there's a very interesting issue here about when we can use two-dimensional analysis and get great results and when we can't. So we took that knowledge that we had from our pressure distributions and the tactile pressure sensors, and we just created a simply supported beam from a number of pipes that were evaluated as shells, and we applied that pressure to it. That's a proxy. When you actually have the soil pipe interaction, the pressure is not a following pressure. It is an intermediary pressure as the soil struggles with the pipe to create some sort of interface pressure at every instance or aspect of the deformation between the two. But in this one, we are looking at it as a following force because if it becomes unstable under a following force because of lateral deformation, that is transverse deformation, then clearly we have to worry about the three-dimensional aspects of things. So we looked at steel. We looked at X52 steel that we've studied and we've used because the pipelines at LADWP are fabricated with that. We have a great relationship with them. We also looked at cast iron because pipelines are affected in urban environments, and they are the most fragile and most problematic. You can look at these cast iron pipelines, again, with a rectangular hyperbola. And you see, when you look at cast iron, even though it's brittle, you should look at it as strain-based. I mean, clearly, pipelines which are ductile have to be looked at as strain-based. But even brittle ones, and you can see that all these tests, we did tests of a pipe that came out of the ground, was there for 50 to 100 years. And these are the tensile stress-strain relationships. And you can see some of them are failing at about 0.25 to 0.3%, about 2,500 to 3,000 microstrains. So we don't really like to see strains in cast iron go up much higher than about 600, and certainly no higher than 1,000 microstrain. So when we look at these steel HDPE cast iron pipes, and also look at them not only from that simple model of simple beam loading, but to prove that that model is giving us a reasonable representation of soil pipeline interaction, we actually ran a couple of these things for pipelines crossed perpendicularly by the fault. What you can see here is the pipe nominal diameter plotted on the horizontal axis and the diametrical strain, the delta D over D, the change in the diameter with respect to the original diameter in the transverse direction, plotted on the vertical axis, and at about 24 inches for both the cast iron and the steel. As we go from 24 to 30, it becomes unstable. That is, you actually start to get transverse ovaling. That ovaling will eventually cause a collapse or crushing of the pipe. For a following load, if we take that as a representative condition where three-dimensional effects really have to be worried about, what we can say is that when you're 24 inches or below, you can get a really good model out of the beams. But when you're getting 24 inches or greater, regardless of your D over T, you've got to be careful about those conditions. And these are some of the three-dimensional results. I have to really give credit to Vesoris and others for their excellent papers talking about this interaction between soil as a solid and the pipelines as a shell. And they have a lot of good recommendations to make there. Ahmed Nisser, who's here in the audience, thank you, Ahmed, also shared with me some of the analysis that he did when he was at MMI. He's now working in his own company, Infrastructure1. And this was for the San Francisco Public Utilities Alameda Siphon number 2, which had to be designed across the Calaveras Fault, take about 4 feet of deformation. And they found that ovaling for that really controlled the design. So they actually had to do three-dimensional analyses until they got to a wall thickness that could keep the ovaling to a reasonable location. So we see this dichotomy in the analysis, and I hope that this paper will provide some guidance with respect to when you need to do one kind of modeling relative to others. So we have 2D beam modeling provides an effective soil pipeline interaction modeling, especially for diameters less than or equal to 24 inches, less than or equal to about 16 for the high-density polyethylenes. And we need to consider this transverse pipe distortion when we're 24 inches or larger for the cast iron and steel and greater than 16 for the high-density polyethylene. Let's talk very briefly about next-generation hazard resilient pipelines. What you see there is a picture from the Wall Street Journal. That's Craig Davis from the Los Angeles Department of Water and Power. And he's responsible for resilience at the Los Angeles Department of Water and Power. In fact, they have the resilience mayor. Eric Garcetti is really leading the nation in creating resilience against hazards. And he went to the pipeline industry and asked them if they could provide pipelines that could absorb some of the large ground deformation they expect during an earthquake, and they couldn't provide it. Now, he'd gone to Japan a lot, so he turned to the Japanese, and he gave a big order to Kubota Pipe, and they started to provide pipe. Well, that generated an incredible response from industries all around the world, and what you'll see next are a number of different innovations in geometric nonlinear accommodation of pipelines that have come forward from a number of different companies, and we're testing them all at Cornell. Thanks to NSF and having our large-scale facility, we're the group that's actually validating each one of these and able to provide information directly to the water utilities, and all of this information will be up on our website. So you can see some of the pictures of the large-scale testing at Cornell. There's some really interesting aspects about the next generation of hazard resilience pipelines. This is a picture of one of these expanded bells. So these bells will actually move and then grab. So they accommodate axial extension, they accommodate additional rotation, so they can accommodate bending, and they also can accommodate compression. Here's some of our graduate students with now postdoc, Brad Wham and Pat. In the test box there, we're looking at US pipe type tests. And you can see that these extra large bells that accommodate this deformation are bigger. They're much bigger. A normal bell is in the background there. And one of the things we find is you drop a lot of stress as you're pulling one of these bells through the ground under large ground deformation. If you don't account for that, you will have an unconservative answer. So the model has to account for these additional stress drops as the bells move through the ground. You can see that 8-kip drop there. This is a molecularly oriented polyvinyl chloride, and look at it being deformed over on the right. This is basically created by expanding a mandrel and getting all the molecules to orient themselves circumferentially. That increases the circumferential strength and allows them to reduce the wall thickness. The real key here is the reduction in wall thickness. And what that does, when we did our tests at Cornell, if you look at the pictures over here on the left, we did compression tests, and that thin spigot, when subject to compression, actually folds into the bell portion of the other side. It accommodates compression by collapsing into the bell, even with those restraints in place. Fascinating, and that's because of the reduced wall thickness from the molecularly oriented. So, lessons for next generation hazard resilient pipelines. There's been a paradigm shift in pipeline technology, and this is market-driven research funded by industry. And when you think about it, you really can't have resilience unless you have a market. Because if you only have one supplier, you're not resilient to the economic situation that they could put you in. It's only having a choice that allows you to engineer both cost-effectively and technically effectively. And in order to develop the next generation hazard resilient pipelines, you have to develop the next generation hazard resilient pipeline models, and that's what we're doing at Cornell, because somebody has to design these things afterwards. All right, so finally, pipeline system performance. I'm going to talk a little bit about the Canterbury earthquake sequence. This was a sequence that's still going on. Everybody here probably knows that on Valentine's Day in Christchurch, they had yet another earthquake, and we wish them well because they've had far too many for one community. But this event has been truly extraordinary, not the least of which in that it has really stressed a modern society with about $30 billion, this is US dollars, to be 40 billion New Zealand, 20% of their gross domestic product is one of the repercussions of this to fix up things after the sequence of earthquakes. So the sequence looked like this. On September the 4th, 2010, there was the Darfield earthquake. Then there was the big Christchurch earthquake, which did all the destruction, destroyed the central business district of Christchurch on 22nd February 2011. The 6th magnitude, 13 June 2011. The Christmas Eve earthquake of December 23rd, 2011. And then most recently, this 14th February. We can take through GIS maps of areas of significant soil liquefaction, which were done by the same team, and thereby provide very accurate shapefiles where significant liquefaction was observed. And looking at it for the first three events, you could see that the Darfield earthquake liquefied in significant measure about 52 square kilometers of Christchurch, 96 square kilometers of Christchurch in the 22nd February 2011 event, and about 91 square kilometers of Christchurch in the June 13th, 2011 event. And that's a lot of liquefaction, let me tell you. So a lot of people don't know a lot about Christchurch. So what we did is we created a special model. It's called the San Francisco scale. We could take the shapefiles of liquefaction from the 2011 February 22nd, and we'll just move them right on to San Francisco. So we now know how much liquefaction occurred in Christchurch. It was 1 Frisco large. And liquefaction is a big concern in San Francisco too. So we could learn a lot from New Zealand, and we are. One of the things we're learning, because they had the prescience to do this, was to run high resolution LiDAR before and after each event, So we can get lateral deformations associated with each event in the liquefaction zones and vertical deformations after each event in the liquefaction zones. We can then use the lateral and the vertical to go and do the kind of thing that Boscardin and Cordy did for buildings, where we know that buildings subjected to ground movement, doesn't matter if this ground movement is created by an earthquake or a tunnel, a building's going to respond structurally the same way to the same kinds of distortions. So if we can characterize the deformation from liquefaction in terms of differential vertical by an angular distortion, dividing it by the distance between the 2 points, and similarly with a lateral strain, we can create a unified approach to ground movement effects both on structures and pipelines at the same time. So here's some of the kind of pipeline damage that was observed in Christchurch, massive damage in their water distribution system. So what we can do is we can take the LiDAR flights, we can superimpose them on GIS over the zones of map liquefaction. This is for the 22nd February 2011 earthquake. We can put in the pipeline system because we have that all geocoded, and then we can put in the repairs to all the different types of pipelines at the same time. So we can, for every level of lateral strain and angular distortion, roll up the number of repairs for a cast iron or asbestos cement pipeline and divide it by that increment of deformation by the number of pipeline kilometers that were available to be damaged, and we can get a repair rate relative to both angular and lateral strain. Now, to do this, you have to have a screening criteria. I'm not going to get into this equation, but there are statistical screening criteria. Mike O'Rourke actually had a big hand in helping develop this. He did it for binomial distribution. We expanded it for Poisson distribution, which is a little more helpful, but the idea originally comes from him. And what you can see is an opportunity to screen, because you run into, when you're doing rolling up these big databases, the challenge of having too small a data set for the length of pipeline you have. So you have a statistic, you roll up a statistic which is statistically not significant or robust. And this allows you to define what's robust and not in your data set. We defined the lateral strains because we're looking at high definition, high resolution lateral LiDAR data. That's on 4-meter spacings. The settlement is on 5-meter spacing. So you can create a rectangle, or you can create a square with 4 corners and do a finite element conversion to get the strains in that cell. And from that we can define a unique strain, which is the maximum compressive strain or the maximum tensile strain. So it has the benefit. We don't know if that was the actual strain that the pipeline was oriented to, but it's the unique strain in that vicinity, and therefore, obviously, the damage must be correlated with it. And because it's unique and the other ones aren't, it's a really good parameter to use. So when you do that, when you roll these things up, you get these kinds of regressions, which have very respectable R-squares to them. That means, if you get an R-squared of 96%, that means 96% of the variability of the data is explained by that particular regression. And we can do that both for the angular distortion and for the lateral strains. You might ask, well, why isn't it, when it crosses, let's say for the lateral strain, the vertical axis, why do we get a repair rate? Because shouldn't it be 0 when we have lateral strain? Not necessarily, because there may have been part of the data set that got subjected to differential vertical. So you have to roll them both together to get the complete perspective on this. And that's what you see in this picture here. You have the lateral strains plotted with respect to the angular distortions, and then superimposed on these graphs, you have the various repair rates that one would predict based on the data set. And these, of course, are interpolations that are run on a linear basis. We could run nonlinear interpolations, but I think we're getting ahead of ourselves with over-precision in the mathematical formulations when you do that. One of the interesting things about this plot is, if you look at the cast iron, where we're actually looking at the repair rates, which are in these different colored zones, and their variability both with respect to lateral strain and angular distortion, you'll see that they're very sensitive to lateral strain, but not so sensitive to differential vertical settlement. And if I had had the time to give the part of the lecture on pipeline response to tunneling ground deformation, we've done 25 years of research on cast iron, which is a real mysterious material, and that's all laid out in there. You find that cast iron is very, very sensitive to lateral movement, and it can take a lot more differential rotation in terms of rotation at the joints. So that is quite consistent with what story you would have heard if we were talking about the tunneling effects on different pipelines. We can also take the entire data set for Christchurch. That's for a particular LiDAR run in areas of liquefaction, maybe 4 million of these the lateral strains, and about 3 million and change for the differential verticals, because those are on 5-meter spacings, the strains are on 4. And we can characterize the cumulative distribution of strain as for each earthquake, as you see in this plot here. And we can look at what these next generation of hazard resilient pipelines are able to accommodate in terms of lateral strain if we put these joints in and we set them at the right level at lengths of pipe between 20 and 15 feet, which is the preferred laying length for utilities in the field. And so if I show the range that can be achieved with this pipeline technology, it shows up right here. That is, they're able to accommodate ground strains ranging from about 1.5 to 2% lateral strain, depending upon the length of pipe that you want to use. Here's some of the kinds of pipelines that can accommodate that, sort of shown as a symbol. And that corresponds to these exceedance values for this large-scale field experiment in Christchurch. So you can actually see that using this technology, you're able to accommodate 95% of the deformation that was generated in most of the Christchurch earthquakes taken as a single event. This gives utility operators a lot more confidence because we can actually relate it back to something real and something that's been quantified, so they understand the ramifications with respect to the performance of their systems. So there's the exceedance levels. And then just to finish up, if anyone ever had a doubt about the resilience of polyethylene pipelines, we've been preaching that for years based on the tests that we ran at Cornell. Well, during the Christchurch earthquake, and this is for the 22nd February 2011, the one that really created the most liquefaction, what you see on the left is the areas of liquefaction, prominent liquefaction, superimposed on the gas distribution system. Now, this gas distribution system was a medium density polyethylene. It has virtually the same characteristics as high density, thermally fusion, joined, and so quite continuous and quite ductile. And what you see on the right are the repairs for the water distribution system. There's about 1,700 kilometers of water distribution pipeline and about 1,700 repairs. There's a lot of repairs because of this earthquake. On the left-hand side with the gas, there's only 170 kilometers, but it's still in the areas of pretty significant liquefaction and ground deformation. In fact, we know a couple of locations where they deform quite a bit. And they both have the same pressures. They're both about the same diameters, both carrying about the same pressures. There wasn't one repair in the medium density polyethylene system, not one, for all 4 of the earthquakes. Now, I haven't heard back from this recent one, but I doubt if we'll find any from that either. Whereas the other one, just one earthquake, 1,700 repairs. So finally, an absolute irrefutable full-scale field experiment showing you the ability of the polyethylene pipelines to accommodate quite a lot of deformation, something that the gas industry has known about, by the way, for quite a number of years. So lessons from Christchurch. Extraordinary data set, multiple earthquakes. Imagine having the same infrastructure subjected again. Imagine living there, the poor folks. This is really a hardship on them. But the data that has been produced will help people worldwide. First-time comprehensive assessment of underground lifeline response to liquefaction-induced differential vertical movement and lateral strain, and then unified methodology for building and lifeline damage versus differential vertical and lateral ground movements. Now, for the last part of the talk, which is impact on communities. And I'm going to use San Francisco to illustrate this. San Francisco, as we just saw, is about the right size for liquefaction during the 22nd February 2011 earthquake in Christchurch. And 97% of the building stock in San Francisco are timber-framed structures that are closely located relative to each other, and if a fire breaks out in one of those, within a half hour it's consumed the block. So fire following earthquake is the major threat in San Francisco, and in fact, San Francisco people know that because in 1906, 392 blocks of the city burned down. It's still the largest single fire loss in United States history. Now, there have been bond issues passed in 2010 and 2014 to upgrade the auxiliary water supply system. This is a really major step forward. There's $400 million in each of these. And we helped with the simulation. In fact, we used the data from Christchurch to simulate repairs to the auxiliary water supply that would occur from the deterministic 7.8 magnitude earthquake in which they are upgrading relative to their system. And the way they chose to look at the performance of their system was to divide it into about 40 fire response areas. This is where the fire stations are located. And if you want to do a good job with characterizing community response, you go to that community that knows the most about the response, that is the fire department. So this was a project that worked hand in hand with the fire department. And what you see is fire demand, which was simulated by Charlie Scawthorne, very well known for his expertise in this area, and the pipeline response that was simulated by AECOM with input from Cornell, looking at how much water currently, if you have that 7.8 magnitude earthquake in each of the fire response zones, could be provided. And we took this to the Board of Supervisors and said, here's the state of the system now. We need to make some changes where you have all of these important financial assets, because San Francisco is a major trading location, has big business, major impact there. They have most of their current auxiliary water supply located close there. That's why you still have some green areas there. But we said we need to fix all that stuff. And the Board of Supervisors, to their great credit, said, absolutely not. Everyone deserves fire protection. Not just the wealthy, not just the people that have all the money, not just the people that are privileged. Everybody deserves fire protection. Go back and give us a program of repair and rehabilitation that distributes it to everybody in San Francisco. This is a marvelous lesson. And we could do that because everything was set up. We reconfigured the whole remake and the reconstruction to actually produce this next map. And this will take many years to do, but the next bond issue has already been passed, and a lot of the measures that go into making that green map green for everybody is already on the boards, and part of it is being implemented as we talk. So, to end, I'm almost out of time. I'm not going to go through the summary of all of these things, but these are many of the lessons that we've learned, and I hope I present it as clearly as I can in this talk. But I think the most important of these is really the impact on communities. Everybody in this auditorium should feel proud because what you do has an effect, a positive effect, on a community or a neighborhood someplace. In fact, the very fact that we can stand in this structure without it collapsing and have a safety factor where we can have this meeting owes to our structural engineers. The very fact that the foundations are holding up owes to our geotechnical engineers. So when we look at system-wide response, and all components ultimately add up to systems, our contribution to those systems is immense and extremely important. So in ending this lecture, I'd like to congratulate all of you for doing the great job that you do to keep our community safe and secure and functioning properly. I thank you profoundly.